So, for decades, engineering has had its trusted champions, right? These incredibly powerful tools we use to design literally everything, from bridges to jet engines. But a new contender has just stepped into the ring, and this one's different. It's an AI that doesn't just see patterns, it actually understands the laws of physics.
Just think about that for a second. How do you find the absolute breaking point of a new aircraft wing or figure out if a turbine blade is going to fail without having to build dozens of expensive and, potentially dangerous physical prototypes?
Well, for a long, long time, the answer has been simulation. Engineers build these incredibly detailed digital twins of their designs, and then they throw everything they can at them all inside a computer. This kind of virtual testing is, and I mean this, the cornerstone of modern engineering. It lets them innovate and push boundaries safely and efficiently.
But of course, this old-school method has its own set of challenges. And to really get that, we need to meet the reigning champion of the simulation world. That champion is called the finite element method, or just FEM. And how it works is actually pretty cool. Imagine you take something complex, like an airplane wing, and you basically slice it up into millions of tiny, simple shapes. You create this mesh of what are essentially digital Legos. Then the FEM calculates all the forces, like stress and strain on every single one of those little pieces, and puts it all back together to give you the big picture. It's brilliant, and it's incredibly powerful. But, and there's always a but, right? Creating that perfect mesh, especially for really complex 3D shapes, is super difficult and it takes a ton of time. A lot of it has to be done by hand, and it can become this huge bottleneck in the whole design process. And that's exactly where our new Challenger sees an opening. So this is where things get interesting. Let's meet this new Challenger, which plans to change the game completely.
Okay, so at the core of this whole thing is a concept you've probably heard of, the artificial neural network. A computer model that's kind of inspired by the way neurons are all connected in our own brains. It's designed to learn really complex relationships between inputs and outputs.
But here's the critical twist. You're not training this network by showing it a million pictures of cats. No, you're training it by teaching it the actual equations that govern the physical world, the laws of stress and strain and motion. And that brings us to our Challenger, the Physics-Informed Neural Network, or PIN. See, unlike a normal AI that just kind of looks for patterns in data, a PIN has the actual rules, the equations of physics baked right into its training. So to put it simply, it's not just guessing based on what it's seen before, it's forced to obey the laws of physics, which means its answers have to be realistic.
And this gets us right to the heart of the difference. FEM, our champion, is totally dependent on building that complicated, time-consuming mesh. But the PIN Challenger, it's completely mesh-free. It just samples random points in space instead of building a grid, which means it sidesteps the biggest headache of the entire traditional process.
All right, so we've got our champion and our challenger. How did they really stack up against each other? Well, researchers at Uppsala University decided to find out and put them head-to-head. And these were the proving grounds, two classic engineering problems. On the left, you've got a simple cantilever beam getting pushed down, which is a basic test of deflection. And on the right, something a bit trickier, a metal plate with a hole in it. That hole is designed to create a single point of high stress, which is a super common failure point in real-world parts. So the contest was judged on two really critical things for any engineering tool. First, how accurate are the results? And second, how fast can you get them? So let's get right to it. First up, and you could argue this is the most important round, accuracy. Can you actually trust the AI's predictions? The results were pretty amazing, actually. According to the study, the PINs were able to match the accuracy of the industry-standard FEM simulations to within just a few percent error. That is a huge win for the Challenger. It proves this whole concept isn't just some novelty. It's a real contender. Okay, so it's accurate. That's great. But in the fast-paced world of engineering design, speed is everything. So for round two, let's talk about speed. And here's where the story takes a sharp turn. The study found that getting that high accuracy came at a, quote, substantially higher computational cost. So for a single one-off problem, the old champ FEM was actually way faster. So it's a split decision. The AI is just as accurate, but the champion is still faster. It kind of feels like FEM gets to keep its title. But the story is definitely not over yet, because the AI has a secret weapon. And this is where the true potential of the AI Challenger really starts to shine. It's not about raw speed in a single race. It's all about being adaptable across many races. And that secret weapon is something called transfer learning. It's a key idea in machine learning where instead of starting from scratch every single time, you take a model that's already trained on one problem and you use that knowledge as a head start for a new but similar problem.
So here's how that works. First, you train a pin to solve that original metal plate problem with the hole. Then, an engineer makes a small design tweak. Let's say they move the hole a little bit to the side. Now, instead of running a brand new simulation from zero, you just take that first pin with everything it already learned and just fine-tune it for the new design. And this is the magic part. By reusing all that prior knowledge, the training time for this new, modified problem gets slashed. This is absolutely perfect for how design actually works, with engineers making constant little tweaks. This is the AI's true superpower, not raw speed, but incredible flexibility. And that brings us to the final verdict, really. For one single static problem, yeah, the champion, FEM, still wins on pure speed. But for the actual process of design and optimization, where you're testing dozens of little variations, the challenger, PIN, wins on adaptability, hands down. So maybe the future here isn't about one method delivering a knockout blow to the other. Maybe it's about a team-up. Imagine using the raw speed of FEM for the big initial checks, and then the incredible flexibility of pins for all the fine-tuning and rapid iteration. The real question this all leaves us with is, what amazing new things could this powerful new team build together?